All right, hey, welcome back here. Let's see, we are at day, must be 7, as we continue to move along here. Yesterday, we were in the process and getting close to finish. We still got a little more things to say here about the energy chapter and the conservation of energy chapter. And so I will add to that. And I'll say it again, at the end of that last video there, I wish I would have planned that discussion about the frictional forces better, because that last step there, I just messed it up. But anyways, maybe that shows that I'm human and it wasn't a really good description. But hopefully you still got the main gist of it, except for that last step was a little confusing there. Again, I apologize for that. But I thought I'd also mention something about the exam. You took the exam yesterday, and many of you shot questions during the exam, and so I think I got to those in a timely manner and answered that. And some of you had some troubles loading in on Canvas. I get that, and you emailed me. And so I was hoping to get a chance to start grading those in the afternoon or the evening. I didn't. Yesterday was a crazy day for me. I'll just tell you, I had problems with my car for whatever reason. The battery just decided to die, and so I had battery issues and had to get jump started, and then I put on the charger. And to add to that, my dog had some GI problems, and so we were at the vet for 3-4 hours, got some medicine for her. In fact, I got to go back this afternoon. So just a crazy day for me. And so normally it takes me about 2 evenings, and so I would have done it Monday night and tonight, Tuesday night, and have things back to you on Wednesday. So just to let you know, I'm a little slow. I'll get to it tonight, assuming everything goes well today with our videotaping, and I'll start grading those Tuesday night, and then give me a second night, Wednesday night, to get those graded, and then I'll have those back to you, and you can have an answer. I did get the solutions done, though, last night. It was a little bit on the late side, but I know some of you have already been looking at them. I looked at the viewing, and it looked like this morning there was something like 12 people had already looked at the solutions. And that's good. If you didn't know that, check your email. That was what I decided to do in place of the lab yesterday. And so we didn't do a lab and a filming of the lab yesterday. That was the ballistic pendulum. And so we're going to do that one today. And so I'm just going to shift everything over one day. But I really thought making that video, going through step by step, and just kind of thinking out loud. And so if you haven't got a chance to see that video, I think it can be very instructive. In fact, that was my directions, is treat that as a lab and go through there and go through my thinking. And if your thinking was different, and particularly if it was different and wrong, catch that and see what you've need to learn as you move forward in this class. If your thinking was different but still getting you to the right answer, that's fine too. But it might be nice to see that other way of thinking. Anyways, I thought by putting it on video would be instructive, and if I just sat there and worked it out and then thought out loud, that it would be helpful. So hopefully it was, but I know that's one of the tricks of being successful in a physics class, is learning to think like a physicist, learning to think like the physical science. And that's kind of hard at first. And so I'm sure many of you are still kind of learning that. And that's kind of what the first exam does for students. It kind of, gives them a little bit of either confidence that they've been doing it right, or kind of a wake-up call, like, okay, I see now how I was supposed to think. And so just thinking along those lines of a physicist does take a little bit of effort. And so that's what I'm trying to say. And it's a little different than any other class. And so it really takes some time. So I think seeing that and seeing me do it was a good option. Anyways, that was my call, and I go, you know what, we'll just do that instead of a lab. So that being said, hopefully then you will continue with this, and so on the second exam, you'll be that much more ready for thinking like a physicist than maybe you were here for the first exam. So that being said, let me continue on here where we left off, and we were doing conservation of energy, and so I'll just put that back on the board here. Conservation of energy is the big picture for this chapter. And of course what that meant, and as I was saying, a kind of a nice way to then solve these problems is to say, okay, what is the energy before, and then what is the energy after? And you saw me work on a few of these, and the types of energy that we saw so far is the first one is what we called energy of motion, and so that was our kinetic energy. That was followed by what we might call a microscopic kinetic energy or an internal energy. Let's just call it a heat energy. And so those two we had to consider when we had those carts colliding with each other yesterday. And let me introduce one more. We'll talk about a few more before today's over, but these three are the three big ones for this chapter. And so the final one here, and what I'll call the third one, will give us enough different forms of energy. We can really do some I'll say neat problems, advanced problems, enough really to get us started here. And so the third energy is referred to as gravitational potential energy. And as the name implies, it has to do with gravity and also has to do with what we call the potential. Let me explain here. Why have a 1 kilogram mass? I had one sitting here, and I used it to tie the balloon. That was a mistake. That was the one for the balloon. Sorry. Here's the one I'm talking about. Let me just put it on the edge of the table, and let me kick this off to the side here. Let me actually put it very close to tipping off the edge of the table, but not actually falling here. You see, what I'm getting at is this object, because it is above the floor, has the ability to then be pulled down by gravity. See, because it's not on the floor, it's above the floor. And it has that ability now to fall because there's room, there's height for it to fall. Now, it wouldn't take much for me to nudge it off the edge. In fact, maybe I can even get a little closer before it falls. But if I nudge it too much, like that, it will fall. Of course, if it does fall, there's the force of gravity, there is the distance it fell. And remember, that was our definition of work, force times distance. And so what I'm getting at here is that subtlety in the definition between work and energy. Remember, we said work is force times distance, and then distance in the direction of the force. But as this thing is falling down to the ground, I would say then gravity is doing work, right? Gravity is putting a force on it, which we called weight. It does pull it a distance, and so that would be the height of it. And so work is being done as it falls. But like that silly joke I gave to you yesterday, if there's 5 birds on a wire and 3 of them died to fly for the winter, how many are left? And the answer is still 5 because those 3 haven't actually left. They've only decided to leave. They haven't actually done it. And that was this whole idea of what energy is. Energy is the ability to do work. So we would say that this object up here, just because it's sitting up on a table, just because it's off the ground, we would say it has the ability to do work. It may or may not actually fall, and if it does fall, then we would say gravity is doing work on it. And of course, if it doesn't fall, then we would say gravity doesn't do any work. But we would say it has the ability to fall. It has the ability to have an unequal above or above some reference point. And so we are going to say that this object here then has energy. And to give it an appropriate name, that's our gravitational potential energy. It's associated with gravity. And it's a potential. Potentially it could fall. Potentially it could do work if it fell. And so this is our third piece of the puzzle. And our abbreviation for it will just be PE for potential energy. More appropriate, it should be GPE because it is gravity. So it's gravitational potential energy. And so that too is a form of energy. In fact, believe it or not, you're actually then watching conservation of energy already when I tipped it off the end and it began to fall. Because if I were to say, what would the formula for this gravitational potential energy, I would say along these lines. We will set the gravitational potential energy equal to the work that would actually be done if it actually fell. Remember, energy has the ability to do work. So we're going to say that it's sitting up here on the top of the table. It has the ability to do work. If it actually does fall, as I just did and I pushed it over, then it does work. So we should say that the work done actually falls is the same as potential energy that it has here at the top. And of course, we defined work at the beginning of this lecture as force times distance. And so in this case, because it's gravity pulling it down, the force would be mg, and the distance it goes down would be its height, that it was, above the ground. And so our new equation here for today, going with our new energy, is mgh. mgh is the equation for the gravitational potential energy. And what I want to point out in this equation then is that the energy depends on two factors. Let me take you all the way back to lab number 4. The lab we did last Wednesday. We had that little driver that we lifted up and we dropped it. And the whole point of that experiment was to check to see if this equation was was valid. And I pointed out that in class we would kind of discuss it and work it out. And that's what I just did here. And so knowing now about work is force times distance, and knowing force is mg, and knowing then the distance would be the height, we come up with this formula, which you'll see is a very useful formula, that says the amount of energy depends upon 3 factors, 2 of them which we change: how high is the object and what is the mass of the object. G, the 9.8, we can't change. That's determined, as we said, by the mass of the Earth and the radius of the Earth. I suppose we could say, well, you could change it if you went to another planet. Okay, but that's not within our possibilities here in our lab. We can't change G in our lab. But we did change the mass, we did change the height, and hopefully what you did see when you did the lab was a convincing experiment that said that the gravitational potential energy changed in proportion to the mass, and it also changed in proportion to the height. And so I want to use that here today, now that we derive, and point out here that if I applied conservation of energy to this falling object, I would have to say, well, what it starts with then is equal to what it ends with. So way back at the beginning, if you will, so I'll start it here. And so here's this 1 kilogram that's on this edge of this table. It's getting ready to fall, but it hasn't yet fallen. And for that matter, it's not moving. See, so when it comes to talking about the energy, if you ask me what is the total energy that this thing has, I would say, well, it's all gravitational potential energy. But as soon as it begins to fall, it loses its height. And so coming over here, and before we put in some numbers, I would begin to say here that, hey, what is happening is it's going to lose its height. In other words, as it is falling, it loses its gravitational potential energy. So does that mean it has less energy? No, not totally. But it does have less gravitational potential energy. Did you hear that difference, right? See, I am not saying that the potential energy stays the same. And for that matter, I am not saying the heat energy stays the same. I am not saying the kinetic energy stays the same. What I am saying is the total energy stays the same. So if I add all three of those together, that will not change. And so as the object is falling, it is losing the gravitational potential energy. But at the same time, what else is happening? And coming back to last lecture, we said that the kinetic energy is 1/2 mv squared. And so as it falls, so as it loses gravitational potential energy, it gains kinetic energy. And the total of those two does not change. And so we lose potential energy, but we gain kinetic energy, and the total remains the same. In fact, that's why I brought out two things you can watch here. This bowling ball, which I'll have to kind of move the table out of the way for you to see the bowling ball. But I'll start over here with this crazy apparatus. It was one of the first ideas of people thinking about energy, and they said, well, okay, so what if I start it at a given height and I let it go? And even if the slope going down is different than the slope going up, or I could do the reverse. It's got a lesser slope going down and more of a slope going up. How high will it go? And of course the argument is something along these lines. If energy is conserved, then when you start right here, it has all potential energy. And when you let it go, it loses that gravitational potential energy that goes down. And so that means it's gaining the kinetic energy. And then as it comes over to this side, it's getting height again. So it would be gaining gravitational potential energy. Therefore, it would be losing kinetic energy. And eventually, it should then go, and it won't be perfect, but it should go roughly the same height over here as over here. And this one's got a little bit of rubbing that goes on. So in this case, the height is a little lower because of friction. Because remember, the total energy has to add up. So if we have any friction, if we have any heat energy, then that's going to take away from our height. But if you could kind of imagine this, and that's why the bowling ball works a little bit better, so I'll show you that one next. But if I take this and I let it go right here, it'll go to the same height. Because when it gets to this height, it has the same potential energy that it had over here. And therefore, it must have also zero kinetic energy so that the total remains the same. In fact, another fun question to ask is to say not only will it go the same height over to here, but if there was no friction, no heat, wouldn't it go the same height every time? And we just let it go. Now, as you can see in this one, and it'll also be true with the bowling ball, but not as true, the rubbing makes some heat, and so now we have created so much heat by now that there's really very little energy left here for kinetic or potential, and so that's why right here, we have very little height and or very little speed at any motion. It's all going into heat. And if I let it just keep going and going and going, what's eventually going to happen, and I'll just speed it up, right there, boom, it's going to come to a stop. Does that mean we lost energy? No, because then that energy went to heat. And if you could see then on a microscopic level, you would see what I was showing you yesterday, and that is these atoms that are in this ball might have been starting like this at a slow speed, and now that it's rubbed for a while, they're going at a fast speed. And I'll turn that off again. I told you things real loud. But it does illustrate something you can't quite see with your eyes, that there is energy here. And so when we take into all three types of energy, the potential energy, the kinetic energy, and the heat, the total never changes. And we may lose one kind of energy, or what we really like to say is it may transform from one type into another. And this one's kind of nice because it's transforming from potential to kinetic to potential back to kinetic to potential to kinetic. And unfortunately, heat comes into play here also. Well, maybe I'll put this one down because, like I said, the one that I think you can see a little bit better here is this bowling ball. And a bunch of power cords here. So I'm wondering what might be the best way to move this. And that won't quite get it out of the way, but I think it'll be close enough here. But the bowling ball hanging from the ceiling is kind of the same idea. We just don't have as much rubbing going on. And so if I take this bowling ball off to the side here, and I say let it go, it will swing. And I don't know if you can tell, but it looks like it's about the same height here as the other side. And so over here we got a lot of potential, then it becomes kinetic, although it's still got some potential. But if where in the scene does the bowling ball have the greatest speed? I hope you would be thinking something like this. Maybe you would write down, let me grab my marker here. But you might come over here and say, all right, the object, in this case the bowling ball, starts off with some kinetic and some potential energy. And as it is swinging, potential energy is calculated as mgh, and its kinetic energy is calculated as 1/2 mv squared. And so if this number is to remain unchanged, let me just put the word constant here. Then as it's swinging, that question of where does it go the fastest would be where does it have the most kinetic energy. And so it must have the most kinetic energy when it has the least potential energy. Energy when it has the least height. And so watching this bowling ball, I don't think it takes a science class for people to come to the conclusion that the fastest place where the bowling ball is moving is right here at its lowest point. And so hopefully you're seeing in the math and the physics of the conservation of energy why that would have to be true. The same thing on a roller coaster. If you've ever ridden a roller coaster, you will know that you tend to go the fastest when it goes down to the lowest spot. And then as it goes up, you have more potential energy, so less kinetic energy. And so it's just an example of conservation of energy. And this one has as I said, works a little better than that back and forth. It does some rubbing. I mean, it does have to go through the air. There is rubbing, and then there's that hinge up there that it swings on. So there is some rubbing, and so you will probably notice after these few minutes that it's not going quite as high as it was before, but it's almost. And in fact, kind of a fun measurement and a little bit scary. And face to face, into class, I would welcome anybody. Said, "Hey, you want to come up here and give this a try?" It's kind of interesting and a bit scary, but we'll put our trust into the science here and say, okay, if I stand right here and I put it up against my nose and I let it go, it should come back, whoa, to exactly the same spot. Okay? Maybe even a little bit lower, because not included in this is plus some heat that's created. And so if there's any rubbing going on, and then when it comes to a stop, then the height must be a little bit lower. But without any rubbing, without any heat, when it comes to a stop, it must go back to the same height. And so whether on this side or the other side, it'll come back to the same height. Now, I'll show it to you again, just because it's kind of fun for me to do. Hopefully it won't take too much time here, but right up against my chin here is its height. And so if I let it go, it'll come right back to that same, maybe a hair less, but fortunately not a hair more. I know it's not going to hit me. And so that's the whole idea of this conservation of energy. Now, there's some numbers here, because some numbers are fun to calculate here. And now you can see how the homework's going to work out of this. Is if I were to ask this question, if I were to take this 1 kilogram mass that is sitting on this table, which is about 1 meter off the ground, and I give it a little nudge, a fun question to ask is, what is the speed of this right before it hits the ground? Now, I want to point out this is a slightly different question than what we did in Chapter 2. Chapter 2, we used acceleration and time. I now have height. And so when I have height, energy is a better answer, or a better to get speed than time. Because I don't know how much time it is, but I know how high it is, and I know the energy is conserved. And so I would do something like this. I'd say, all right, here's the before, I drop it. Here's the after. And they have to be equal. Coming over here to this side of the equation, I might start and say, all right, I would have mgh plus, and I'm going to put a 0 there. The 0 would be for the kinetic energy. This object is not moving. Right now, at the top, it has a speed of 0. And so when I go to calculate its energy, I would say, okay, it's 1 kilogram. And just to round things so I can do them a little quicker in my head, I'll put 10 meters per second squared for the acceleration due to gravity. And it's 1 meter. Makes it really easy to multiply. 1 times 10 times 1 is 10. And as we mentioned yesterday, energy is measured in joules. We'll see that again. Here's the kilogram. There would be a meter times a meter, so that's a meter squared, over a second squared, and so that's a joule. So what this is saying here is that this object, as it sits here above the ground, has 10 joules of energy. And I want to convince you that as it begins to fall, that energy does not increase or decrease. It stays the same. Now, what decrease, though, is the potential energy. But at the same time, its kinetic energy will increase. So on this side of the equation, let me put the mgh plus 1/2 mv squared. And let me point out then that as this thing goes all the way down and right before it hits the ground, so really close, it hasn't hit the ground, so it's still moving, but really, really close, I could say that the height is essentially 0. Now you might say, well, it can't be 0 because it would have hit the ground. Okay, so let me put in point 0.0000000000001. Okay, and by the time you calculate that, there's so many zeros. Well, mathematically, it's really, really close to 0. All right, so I'm going to say it has no potential energy. And so that means its kinetic energy would be equal to this 1/2 times its mass, 1 kilogram, times v squared. See, and then that's how I'm going to answer this question. What is the speed right before it hits the ground? So I'm using the big principle called conservation of energy to then find out what is the speed. Okay, so then if I do my 2 over to here, so that's a 20. I do a joule, and let me go ahead and, if you'll allow me, to write a joule out as what it was before I put it all together. And then when I divide by the kilogram, I'm going to get my v squared. So the final step would be to take the square root, and so you can see here taking the square root of both sides, so that's how you get the v. Then you're going to have this kilogram cancels off, and you're going to have numerically the square root of 20. I'll need my calculator for that one. And so square root of 20. And so that's a 4.47. And then looking at the units, the square root of meters squared would be meter, and the square root of seconds squared would be second. So good, my unit analysis works well. Right? I'm expecting to get meters per second because the question is, what is the speed? And sure enough, I worked out my units, and the units work out right. And that gives me confidence to trust the number. And so I would say that the speed right before impact is 4.47 meters per second. And that's probably the easier one. How about this one? What if I changed the question a little bit? What if I said, what is the speed after it has fallen 30 centimeters? Now maybe drawing a picture might be worth it here. Okay, so here's the 1 kilogram mass up here on the table that is 1 meter high. And I push it off the end, and it drops 30 centimeters. And my question is, what is the speed now at this point? Now, part of this would tell me, well, it must be less than the 4.47. I mean, that's the number I got when it got all the way to the bottom. And that's true. All right, fair enough. But I want you to see then, this principle of conservation of energy is powerful because it doesn't just say that the energy at the bottom equals the energy at the top. It says the energy are equal everywhere. You could have fallen 5 centimeters and we would say the energy is still the same. Or it could be halfway down or 3/4 down. I just picked 30 centimeters. But using this same idea, I should be able to answer the question, where is the speed really anywhere on here? Using the principle of conservation of energy. And in fact, as you'll see, we just calculated that the energy at the top is 10. And so I'm trying to claim here that the energy would be 10 everywhere. 30 centimeters down or 50 centimeters down or 70 centimeters down. It still has a total energy of 10. And knowing its total energy, I can then figure out what its speed is going to be. Well, watch, here's how the table and the calculation would work. And so if I go before, after, and the before is really kind of the thing we did here. Before would just be the mgh plus 0. Again, the 0 because at the top of the table there it has no motion, no kinetic energy. And then, of course, this would be the 1 kilogram with G equaling roughly 10, and the height being roughly 1 meter, comes out to be 10 joules. And so that's not new. That's the same thing we did over here. I'm just asking a different point. Instead of saying all the way down at the ground, what is its speed, I'm asking for its speed after it has fallen 30 centimeters. So on this side of the equation, I would have an mgh and also a 1/2 mv squared. And so that's what I'd want to find right here. What is the speed? And of course, what makes this one a little different calculation is we won't have a 0 here, right? I'm not saying the height is 0. The height is 0. And that's really what might make this a harder problem, because when I put in the mass of 1 kilogram and I put in the g of 10 meters per second, let me pause right here and have you think about it. What is the height? Because I gave in this problem deliberately the 2 common mistakes students make. And one of them is using the distance in centimeters. We don't want that. We want our distance in meters, right? We know that back here. If energy is measured in joules, then what is inside of a joule has these units: a kilogram, a meter, and a second. So when we're dealing with energy, we want to make sure all of our distances are in meters, all of our masses are in kilograms, and all of our times are in seconds. And so I deliberately gave you centimeters to make sure that I got a chance to point out, do not use centimeters, use meters. All right, so I'm going to change my 30 centimeters to 0.3 meters. Okay, then the second thing I wanted to point out is, notice the energy is based upon the height. Is 30 centimeters or 0.3 meters the height? No, that's L. Its height then would be the 0.7 meters. And so be careful with that and the way it's phrased. But the gravitational potential energy is calculated based upon its height. And so I phrased it as how far it